Hey, good morning, everybody, or good afternoon, whenever you get to hear. I guess it is almost noon as I'm recording this. Um, pardon me. This is lesson 6.2. This is the disk method for finding volume. We will use integrals to find the volume of a solid of revolution. So this is a little tough. I'm sorry we're not in person for this. But yesterday we were finding the area between two curves. So I'm going to come over here to the side. So what happens today is we find an area. It goes down to the x-axis, whatever this is. I'm going to take my shaded region here. And then I need you to imagine this whole shaded region rotating around the x-axis. And so when that happens, you get this 3D shape. There's the top, there's the bottom. But again, imagine this rotating. You've got lots and lots and lots of slices. So right now mine kind of looks like a seashell. Think of like a lemon that's sliced up, whatever the shape is. This is called the disk method. So there are two ways to calculate volume of rotated objects in calculus. One is disk and washer method, which are combined. We're going to do them in 2 different days. And the other one's a shell method. I wish we had time to go over that, but we don't, but that's okay. The disk and washer method are important for whatever you're doing next. So what you have is a whole bunch of itty bitty disks stacked on top of each other. And just like our rectangles, if you get enough of those and small enough and get them smashed together, say an infinite number of them, you can create this solid. So that's what's happening. So it really is a cylinder. They're just really short, fat cylinders. Think like a tuna can cylinder instead of a can of tennis balls. Short and I don't know, wide. So here's my cylinder. Let's go to yellow. My cylinder's over here and my volume is pi r squared h, or whatever order you have that in. So you can look that up anywhere online. That's from geometry. But that's the basis of what we use in calculus. So here's your pi. The height of this cylinder, remember this is a really, really short cylinder, not like shown in the picture. Your height becomes the dx. Sorry, I'm getting my colors all mixed up here. So height is really your dx. If you pretend it's really, really short. And then finally, that radius squared is the piece that's in here. And that's the piece that gets integrated. So you have r squared and your radius squared. So that a to b tells us where I start my area and where I end my area. So they're pretty cool. Now, draw the region to rotate, determine what type of rectangles to use. We can have vertical or horizontal. We're only going to do vertical in this class. Determine the radius. So example 1, this is kind of what my quick sketch was. Find the volume generated if the region bounded by f of x equals sine of x on the interval 0 to pi is rotated around the x-axis. So let's sketch this in here. Pi for reference is 3.14. You know that though. Your sine curve only goes up to the value of 1. So probably not the best coordinate plane to show it on, but there's sine. Something like that. So it's also bounded by the x-axis. So the shaded area that we're looking at is this. So you have to imagine that shaded area spinning around the x-axis like this. And again, you'll get that lemon shape with slices on this one. So my volume formula is pi from A to B r squared dx. And these will always, always, always have dx for us in this class. Outside of this class, you will run into a dy as well. So here's volume. A is going to be 0, B is going to be pi. That's already given to us. Your radius, this is why I use that funny looking stick figure. The radius is the height of the stick figure this time. So its head is at sine of x and the feet are at 0. Square that quantity, dx. Now, this one, if I rewrite it without the parentheses, I have sine of x squared. yesterday, I know that you could calculate some of these by hand. Not going to be a possibility today. We can't integrate sine squared. You don't have an antiderivative for that, and that's okay. We don't need one. We're going to use Math 9 instead. So I know I have my camera off today, but I'm popping over to my calculator. I'm doing math, the number 9, which is n derivative, and I have an 84, so my calculator pops up with the integral sign. I'm putting in 0 and pi. Inside, I'm putting sine of x. Now, what you put in your calculator and what you write don't necessarily match. That's one of my frustrations here with the TI. So let me come over here. So we know that the quantity sine of x squared looks like this. Your calculator forces that left parenthesis first. That's okay. You can close the parenthesis. And then if you square it, calculator. If you square it, these two things are the same in your calculator. You can also in your calculator just give it an extra set of parentheses, which sometimes is nice. Sine of x, close the sign, square it, and then you have the end of your integral. So it's up to you, but you won't be able to put the 2 right on the sign. It doesn't work that way. So when I do my integral, I have 1.571. I still have the pi in the front. I haven't multiplied. So when I multiply 1.571 times second function pi, my final answer is 4.935. And it's units cubed, but we don't really have to worry about the unit piece. All right, looking good, my friends. Example 2, find the volume generated by revolving the area bounded by all this stuff around the line y equals 1. All right, so the square root of x plus 1 is your square root curve, but it shifted up 1. X equals 4 is a vertical line over here at 4. And y equals 1 is this one. So the region that we're talking about is everything in here. So our formula is still the same. It's still volume equals pi from A to B r squared dx. So pi sits in the front. My A, even though they didn't give it to me directly, is going to be this point, which is x equals 0. My B is over here at this point, which is x equals 4. Now your radius, when we were talking about head minus feet in the area lesson, this is where they start to combine together. Your top is the square root of x plus 1 minus the bottom, which is 1. This whole quantity needs to be squared, dx. So if I clean this up for you a little bit, I've got pi from 0 to 4. Square root of x, 1 minus 1, that's 0. Quantity squared, dx. Well, what happens when you square a square root? It's just x again. So x dx. Now, again, you're completely capable of doing this by hand with the fundamental theorem of calculus, but I think we're all ready for math 9. So math 9 from 0 to 4. X goes on the inside, dx problem. I have 8. Whoops. Eight times pi, 24, or excuse me, 25.132. All right, I think I have one more example for you, and that's it. Yep, example 3. Find the volume of the solid that results from the region bounded by 9 minus x squared, square root of that, and the x-axis is revolved around the x-axis. So if you don't know what a curve is, that's okay. You're just going to use your graphing calculator or your iPad to help out. I've done this problem enough times. I know it's a semicircle with a radius of 3. So a lovely semicircle, not that lemon shape or football shape we had before. And then the x-axis is down here, is revolved around the x-axis. So my volume, still pi from A to B, radius squared dx. The area that's being rotated is this one. We're going to rotate here. So I know we could set them equal to each other and do all that stuff, but I'm going to go on the fact that if I put a 3 in here, 3 squared is 9, 9 minus 9 is 0. I know that this is the point of start. That's my A. And there's my B. My radius, here's my little stick figure, top minus bottom. Usually at this point, my calculus students still don't trust my stick figure, but the more problems like this we do, this starts to grow on them. So this is the square root of 9 minus x squared. This time the feet are on the x-axis, which has the equation y equals 0. So we don't have to put that 1 in there. So if I clean this up a little bit, goodness, a silly cough. We have 9 minus x squared. I don't have to worry about the 0. This is squared dx. This would be 9 minus x squared dx. And again, you could solve this one by hand with fundamental theorem of calculus, but math 9. 9 minus x squared dx. So this is pi 36. $113.097. So there you go. Now, the problems, I've already drawn you the pictures so you don't have to worry about what they look like, which is great. And it honestly looks like you can figure out the A and the B, you know, without having to set them equal to each other, which is also very terrific. Use Math 9 for all of these. I'm just looking. All right, and I just have 2 trig functions for you on the bottom. I know the pictures look a little bit funny, but just treat them like all the ones before that and you will be just fine. I wouldn't try to solve these by hand, but in your calculator, again, remember that you're in radians. And that really applies to my students who hop back between physics and calculus. Physics, you use degrees. Calculus, you have radians. So good luck. Thanks for your patience. We're going to do one more lesson tomorrow. That's it for lessons. We'll figure out something for an assessment for this unit. Review for a final, and there we go. We're done. So thank you, thank you, thank you, thank you. Feel free to email me with any questions anytime. All right. See ya.